So, ladies and gentlemen, let's continue with degrees of specifications and its relationship to control. The idea being to emphasize that there is a very intimate link between degrees of freedom, what you specify to exhaust those degrees of freedom, and implicit in those specifications is a control structure. So, control thinking, degrees of freedom thinking, and what to specify, these things all go together. That's the basic purpose behind this lecture. So let's go back to this toy process A plus B goes to C. And we saw last time the control degrees of freedom is 9, the steady state degrees of freedom is 6. But let's assume we don't know anything, we are novices, and then what we do the simplest possible thing. And the simplest possible thing to do is, well, run the process with the operator specifying directly the valve positions of all the available control valves. So the operator would be specifying all these control valve positions. I hope it is obvious to you that with this sort of a situation, the process can't run, because if you look at this guy, two streams are going in and a recycle stream is going in, and so if you look at the reactor, there's 3 streams that are going in, 1, 2, and there's this guy that's going in, and these are all independently set. And then you're independently setting this guy. Obviously flow out is not likely to be equal to flow in, so the level of this reactor is not going to be stable. Similarly, enthalpy in and enthalpy out and the heat being removed. So enthalpy in, enthalpy out, heat being removed and heat being generated due to reaction, this balance will also not be closing, and therefore the reactor temperature will also be drifting, and so on and so forth. You look at any unit and you'll see that with this kind of a running scheme where you're just allowing the operator to directly set the valve positions, there's going to be a lot of trouble, because none of the balances are automatically closed, and because they are not automatically closed, the operator will go mad moving this valve, that valve, to keep this level, that level, this temperature, that pressure fixed, yeah, to not allow a drift in these entities. So obviously this is not a good way of doing things, and so with this kind of a scheme, you'll have drifting material energy inventories. The process will never be steady, and it is guaranteed that one or more safety limits are going to get violated. This is not the way to run this process. Okay, no control is not an option. So now you need a control system so that basic material energy balances are closed robustly. And so we say, okay, let's do the minimum possible to close all possible balances, independent balances. We're going to move these valves to close different balances. So now what we do is, instead of specifying valve positions, we're going to say, okay, what we have now is FA is fixed, the flow controller is fixing FB, reactor temperature controller is fixing T reactor, level controller is fixing the hold up in the reactor, on the column reflux rate is fixed by this flow controller, steam rate is fixed by the steam valve position, and you also have, maybe we should use a different color here, you also have pressure of the column, hold up in the reflux drum, and hold up in the sump. This is the next level of control that we are implementing. So now the question is, will the process be attain steady state? If I start thinking about it, well, this level controller will fix the material balance on the process, this level controller on the reactor. This temperature controller will fix the energy balance on the reactor. This level controller will fix the material balance top of the column. This level controller will fix the material balance bottom of the column. The pressure controller will make sure that energy in whatever vapor is generated gets condensed, so this will close the energy balance. So pressure controller of the column is fixing the energy balance on the column. Whatever steam rate that we're putting in, according to that we'll have a product. Of course its quality will be whatever it is, we are not doing any quality control, so the product will be whatever it is. And similarly the amount of impurity in the top will be whatever it is, because reflux is fixed. Now if you look at the overall plant balance, what you're doing is you're fixing flow A here and you're fixing flow B independently here, and then product C is being taken out under level control. Whatever accumulates at the bottom of the column, if the level rises, that is what is being drawn out as the product. So if I set this at 100 kilomoles an hour, and let's say I set this at 110 kilomoles an hour, even though I know they should be equal, I may set them to be equal, but then 10% flow error is very routine, so they may still be off by 10 kilomoles an hour, so that's fine. Then at steady state, do you see that A, because there is no quality control here, you will get substantial B impurity, and we are assuming that A is light, B is intermediate, C is heavy. So B being closer boiling to C, the principal impurity in the bottoms will be B. So there will be substantial B impurity going out, and there will also be substantial B impurity going out because you are putting in 110 kilomoles per hour of B and only 100 kilomoles per hour of A. So the 10 extra kilomoles, they will have to find a way out. So that 10 extra kilomoles per hour has to get out of here. So yes, a steady state will come, but you will have substantial B impurity in the product. You will have no control on the product purity. So no quality control on the product is the problem with this control structure. Okay, so that's that. So here the specifications are FA, FB, T reactor, V reactor, reflux rate, steam rate, column pressure, volume of the reflux drum and volume of the sump, and the process will settle at steady state because the material and energy balances are being closed, and there is also a way possible for the overall material balance on the plant to close, because the excess A or B will have a way out down the bottoms of the column, because we are not trying to control the product purity. So whichever component is excess A or B, that excess A or B will find its way out down the bottoms. The flip side is high product purity is not possible. In fact, there is no product purity control. The product is as pure as it is. You can't guarantee the customer that, or claim a guarantee that, look, my product is 99.9% pure. With this control system, you can't make those kinds of guarantees. So yes, these specifications are possible, and corresponding to these specifications, the control system is in front of you. It will settle at steady state. However, product quality control is not possible. Okay. So now we say, okay, let's try and fix this problem. And now we say, okay, we'll have a temperature controller here. That will give me quality control. And we also have B in ratio with A. So FA is fixed, and this set point is, I'm fixing the B by A ratio, FB by FA. So in addition to the other specifications, now I have implemented additional loops, and the additional loops are a temperature controller on the column which is manipulating the steam duty. Earlier I was just specifying Q, but now Q is being manipulated to hold a stripping clear temperature, and I'm holding B in ratio with A because I know 1 mole of A reacts with 1 mole of B to give 1 mole of C. So in this case, my specifications are FA, FB by FA, the ratio set point, temperature of the reactor, volume of the reactor, reflux to feed ratio, temperature of the column, and then of course P call, column pressure, volume of the reflux, hold up of the reflux drum, hold up of the sump. These are the specification variables corresponding to the control structure that is shown to you. Okay. Problem here is that, you see, FB will not be equal to FA even if I specify that the ratio FB by FA on a molar basis is 1. It's not going to be equal. Because it's not going to be equal, let's say there's 5 moles excess A. That excess A is going to accumulate in the recycle loop because the temperature controller will keep on cranking up the steam, and so the excess A that is coming down, it's going to get sent back up because the boil up will be increased, and so the excess A will build up in the recycle loop. So there is one drifting inventory whose the overall material balance is not being closed in this case, because I've got those two feeds and I've got C going out. I'm specifying this FA and I am holding FB in ratio with A. So if I specify this to be 100 and I specify this to be 100, but the actual value of this guy because of flow errors is, let's say, 95, and the actual value of this guy because of flow error is, let us say, I don't know, 105, you got 10 extra moles of B entering the process. The temperature controller is not allowing those excess moles of B to drop down. Therefore, the excess B will keep accumulating in the recycle loop until either the column floods or some constraint gets hit, some valve fully opens and so on and so forth. Most likely the column will flood. So this is the problem with this control structure. The overall material balance for the process is such that, let's assume the product is nearly pure C, negligible A and B in the product. So what that means is, you've got A going in, you've got B going in. The A and B are allowed to leave only as C. That's the structure of the process. That's the structure of the overall material balance on the process. That being the case, if you specify this to be 100, you cannot specify this, because if this is 100, this has to be 100 and this has to be 100. That's automatic. You're not free to specify both the feeds if you're having tight product quality control, if you're having a highly pure product stream leaving the process. Yeah, this is very similar to the tank, where you cannot specify both the inflow and the outflow. You can specify one of them and the other stream has to be under level control, so that in is equal to out. Similarly, in this case, There is an overall material balance constraint that relates these three streams, and therefore only one of them is independent. It can be said independently. The others will have to be such that the overall material balance on the process is specified. This control system that is there in front of you, it is making the mistake of specifying both A and B independently when only one of them can be specified independently. So the process will not be steady. Whichever component feed is being sent in excess, that will accumulate in the recycle loop as shown in the figure, and that particular inventory is drifting all the time. Just like in a tank, if inflow is not equal to outflow, exactly the tank level is drifting all the time. Yeah, so it's the same phenomena. The tank example is trivial, and this phenomenon of the need to stoichiometrically balance the fresh feeds. The fresh feed should be such that fed in a manner such that the reaction stoichiometry is perfectly satisfied. This is a material balance constraint, and my control system must honor it. And this control system, the way it is drawn, is not honoring it, and therefore with this control system there is a possibility of stoichiometric imbalance. In fact, stoichiometric imbalance will always be there. So the excess reactant will accumulate in the recycle loop. Therefore the process will never be steady. There will be a drift in the recycle rate of the excess component, and therefore this control structure as is shown there is guaranteed to fail. Note that in a simulation, even in a simulation, you can make a mistake in specifications, because the point that I'm trying to make is, see, you're specifying FA independently. This is indirectly specifying FB. So let us say you're running HYSYS or Aspen Plus, and let's say you specify this to be 100 kilomoles per hour, and let's say you decide, okay, let this be 101, and let us say this is 99.99% pure C. Okay, what will happen? The recycle loop will never converge because of this mismatch. Then you say, okay, let me be a smart cookie. I realize that there is an excess of A or B. There's an excess of B, and excess of B cannot be there. So let me say I'll specify this to be exactly 100, and exact values can be specified in a simulation. What will happen? The simulation will converge, and there is a recycle tier here. Whatever is the recycle rate that you specify, say 500, the recycle tier will converge around that. If you specify the recycle tier at 1000, it will converge around that. The problem is, we are thinking that we are specifying FB, but actually we are specifying something that is dependent, and we are specifying in a manner that that dependence is satisfied. What is the dependence? That flow A should be equal to flow B. So we are specifying flow B is equal to flow A. That dependence, so there are 6 degrees of freedom. We think that we are specifying 6 things, but actually this is a dependent specification. So this is not really a specification, and therefore it's like if there are 6 variables and 5 equations, you get infinite solutions. That's what you'll have here. The recycle tier will converge at whatever is the guess recycle rate that you have given. So you get all these spurious solutions in a simulator, and this is because what we think is a specification is actually not really independent, it's actually dependent. Specifications have to be independent. 6 independent variables have to be specified. These 2 specifications are dependent, they should not be specified, and that's that. And if you deliberately specify that, if it is not specified in a manner that respects overall plant material balance, the recycle tier will never converge. And if you somehow understand that okay, this and that must be equal, and you specify FB to be FA, that's equivalent to under specifying, and then you'll get infinite solutions. Whatever is the guessed recycle rate, around that is where you'll converge. So one has to be very cautious in what you specify and how you exhaust your degrees of freedom. So this particular control structure as it is shown looks reasonable, but is actually guaranteed to fail. Okay, now let's keep going forward. So now we realize that the problem is stoichiometric imbalance. All the other balances are closed properly, but the stoichiometric feed imbalance is not being closed, and so we need a loop to close that imbalance. So what we do next is put in a composition controller. See, if a component is in excess, that particular inventory will keep rising, because that particular inventory composition will keep rising, just like tank level. If in is not equal to out, tank level will keep rising. If the two feeds are not stoichiometrically balanced, the excess component, its composition will keep rising, and the other components composition will keep going down. So let us say in here we are trying to control B mole fraction, XB is being controlled. We're giving it set point, and in order to keep the B mole fraction in the reactor at set point, we adjust the A by B, fresh A by fresh B ratio, or rather fresh B by fresh A ratio into the process. This control system also closes the stoichiometric imbalance, which was a drifting mode that one had. So this control system will work. Specifications are in front of you. Let's see FA XB reactor, T reactor, V reactor, L by F, temperature of the column, or stripping tray in the column. These are the 6 steady state specifications, and then we have P-call, volume of the reflux drum, and volume of the sump. So you see this control system corresponds to those specifications. That's the point that I've been always trying to make, that you've got degrees of freedom, and in order to reach steady state, in order for the process to end up at steady state, you need to understand material and energy balances and make sure that all independent material and energy balances are closed. And in order to close those material and energy balances, you need to specify appropriate variables. Every specification that you make is equivalent to a control loop controlling that particular process variable, and therefore degrees of freedom, specifications, and control structures, these are all linked, these are all related. Yeah. So now we continue. For this control structure, all independent balances are closed, and this will drive the process to steady state. So this is a control structure that will work, that will drive the process to steady state, because it is closing all the independent material and energy balances. Okay, let's continue. Now we say, okay, let's because we want tight quality control, maybe we have a composition controller that is specifying the C purity level, XC in the product, mole fraction of C in the product. You're controlling the purity of the product, and this composition controller is manipulating the column tray temperature set point. So that's an additional loop that put in. And let us say we also put in another loop, and that's shown here. And let me explain to you what's going on here. What we are doing here is we are measuring the composition. We are measuring the composition of A. So this is a composition indicator, is giving the composition of A. There will actually be a lag here, which is not shown because we sort of ran out of space, but there will be a lag here which will be a tuning variable. So this composition is multiplied by XB by XA set point, the B to A ratio in the reactor. So this is like B to A excess ratio or under ratio, depending on whether reactor should operate in A excess environment or B excess environment. So the B by A ratio you multiply by this guy, and that gives you the set point of the B composition in the reactor, and this composition controller then adjusts the B by A ratio of the fresh feeds. And in this way what you do is you are trying to maintain the B to A or A to B ratio in the reactor. Okay, so that's what is going on here. So these are the two additional loops that we put in, and for this case the specifications are as before. FA, sorry about the color, XB by XA for the reactor, T reactor, V reactor, L by F over here, and XC product. See, these are the 6 steady state specifications, and then of course you've got Pcall, volume of the reflux drum hold up, and volume or hold up of the bottom sum, V sum. Yeah, so see, this control structure corresponds to these specifications and these loops. Sorry. Let's continue. In this case also all balances are closed. This structure will also drive the process to steady state, and maybe later on this control structure and the previous control structure, how do they differ? They differ in what is being controlled. In the previous case, XB reactor was being controlled. In this case, this is what is being controlled. In the previous case, temperature of the column was being controlled. In this case, product purity is being controlled. So the two specifications corresponding to, one corresponding to the column and the other corresponding to the feed balance, to one of the two feeds. These are the two specifications that are different between previous control structure and this control structure. And of course, what you control, if you control different things, the economic performance of the process, depending on what is being controlled, is going to be different. And maybe later on I'll show you that this particular arrangement will give you economically optimal operation or self-optimizing operation. We will do that later. But as far as stabilizing the process at a steady state is concerned, both of these control structures are fine. Okay. So let's continue. Next thing that I wanted to highlight was, and this is maybe partly obvious, but it will become more obvious as we go through the next couple of examples. So you've got X degrees of freedom. So you need to specify X process variables. There's tremendous flexibility in what you can specify. Of course, there are good specifications and bad specifications, But the point is, there remains tremendous specification flexibility. For example, for this very simple splitter, where a feed flow is split into 3 flows, the way the control structure is drawn there, the specifications are flow in the first leg, flow in the second leg, flow in the third leg. First split, second split, third split. Yeah. You could have, for example, this guy. So here what we are doing is F2 is kept in ratio with F1 and F3 is kept in ratio with F2. You see, this is F3, oh sorry, F2 by F1, and this chap is F3 by F2. So now what you're doing is, instead of specifying F1 and F2 and F3, the specification variables in this case are F1, F2 by F1, F3 by F2. Is this the only combination? No, I think there are infinite combinations. You choose. Here what we are doing is, you're taking the flow set point. F1 is independent. You're taking this set point, summing F2. So F1, so the output of this guy is F1 plus F2. You're taking the negative of that, so you're subtracting that from F dot. This assumes that F1 plus F2 is less than F dot, and this is the set point. This set point is actually F dot minus F1 minus F2. This is being given as the set point for the third split. Okay, so in this case, the specifications are F1, F2, and you're keeping F dot fixed. So the third flow is adjusted so that F3 is equal to this, and what that means is, that's equivalent to specifying F dot is equal to F1 plus F2 plus F3. So if F dot is specified, if this is specified, this is made dependent. Yeah. So the specification variables in this case are F1, F2 and F dot, and you can have infinite such combinations. I can have quadratic, exponential, I don't know, hyperbolic, whatever function you want, you can program that. Yeah, so there is tremendous flexibility in what you specify corresponding to the degrees of freedom that are available to you. Okay, in fact, infinite flexibility. Let's continue. Now let's look at a distillation column. The way it has been drawn here, we have feed flow. Maybe I should change the color. Yeah. We have feed flow, reflux flow, and Q. So F, L and Q, and then of course we are also specifying P call. We are also specifying P call, PRD and V sump, but these are not things that affect a steady state, or for example P call set point cannot be adjusted, so we will not talk about that. As far as the steady state degrees of freedom of the steady state specifications are concerned, the steady state specifications for the control structure, simple control structure that has been shown, are F, L and Q. F sets the processing rate, of the process, which is a simple distillation column. L and Q are things that I may adjust in order to get the kind of split that I want, the kind of purity that I want in the distillate and the bottoms. So L and Q are handles that I have for adjusting the column split. F fixes the processing rate. Is this the only possibility? No. Again, depending on what we want to control, there are infinite possibilities, and let me just show you a few. We have the same control structure, but now what we do is very commonly done. The reflux is maintained in ratio with column feed, and a stripping tray temperature, S for stripping, is maintained by adjusting the reboiler duty. So in this case, of course, I have the feed that is specified. So in this case, the specification variables corresponding to my steady state degrees of freedom are F, L by F, and T stripping, TS or T call S. Yeah, so these are my specs. Now I have the same control structure as in figure 2, sub figure 2, and now what we do is we put in two composition controllers, and these composition controllers are shown there in the figure, and what we have is purity of the distillate is being controlled by this controller by adjusting the reflux to feed ratio. Purity of the bottoms, X bot, is being controlled by adjusting the stripping tray temperature controller set point by adjusting this chap, and this guy is adjusting this chap. Yeah. So in this case, my steady state specifications are F, X bot, and X distillate. These are my specs: F, X distillate, and X bot. Yeah. Are these the only possibilities? No, there are tons of possibilities, and let me just show you 3 more, and then maybe I'll end the lecture. So continuing, now in this case, what we're going to do is, instead of specifying the feed to fix the production rate or the processing rate of the process, we're going to specify the reboiler steam. It is the reboiler steam that will fix the production. So what we are saying is, V set point is fixed. Oh, sorry. Oh, well, sorry. So Q set point is fixed. Reboiler duty is fixed. In other words, because reboiler duty is setting production, now the reboiler duty cannot be used for tray temperature control. And then what we are doing is, we are keeping as before reflux in ratio with the feed, and there is this tray temperature controller which is manipulating the feed rate in order to hold the tray temperature. How does this work? It works as follows. If I increase the reboiler stream, the boil up will increase. As I increase the boil up, the tray temperature will go up. If the tray temperature goes up, the temperature controller brings in more cold fresh feed, and as more cold fresh feed comes in, the tray temperature goes back to set point. That's how this control system works. So in this case, my specifications are Q, L by F, and TS, And the point that I wanted to make was that this guy Q sets production, sets the processing rate, and the processing rate is also referred to as throughput or throughput. Okay. Uh, let's take this a bit further. Look at the next. And I think what I'm trying to do here is, instead of setting production using the boil up or the reboiler duty, we're going to set production by fixing the distillate rate. Why would you want to do that? You may want to do that because let us say the distillate is feeding into a downstream unit which is very fragile. That means if the flow changes a little bit, if any disturbance goes into that unit, it's a fragile unit, it's very hard to stabilize it. So you don't want to unnecessarily disturb that unit. So instead of fixing the column feed, what you're going to do is we're going to fix the feed to that fragile unit, and the feed to that fragile unit happens to be the distillate of this column. So now what we're going to do is processing rate is being fixed at the distillate. That being the case, now see, how do I control this level? The reflux drum level. The simplest way, somebody may say, okay, let me do the confusing way. Somebody may say, okay, do it this way, control the level this way. Well, the light material accumulates at the top of the column. If this level goes up, what should I be doing? If this level goes up, I should be taking it out. But I can't take it out because this distillate is fixed. So if this level goes up, I should be bringing in less feed. That's what should be happening. What I'm doing here is I'm basically recirculating the material back into the column. And if I recirculate the material back into the column, the only way of adjusting the feed is to adjust the tray temperature by manipulating the feed. However, the tray temperature response to liquid flowing down is going to be very slow, and let's say I'm controlling a stripping tray temperature as usual. This time lag is going to be very large, and therefore it is possible that by the time you cut down the feed, this reflux drum level, because there's only a 5-minute hold up, by the time you start cutting down the feed, 10 minutes may have gone by, and this reflux drum may have overflown or run dry. So yes, it can be done that way, but this is a sort of gives you a long loop, so this is not what one would recommend. The simplest way is the dynamically fastest way, and the way that makes sense is shown in the figure. Whoa. Okay, and it's shown here. Maybe I should explain it to you and then bring it in. What if you do level control this way? If you do level control this way, imagine distillate goes up, level starts to go down, the level controller cranks up, level starts to go down, the level controller cranks up the steam cranks up, more volume, more vapor boil up in the column. As the vapor boil up increases, the tray temperatures start to rise, and then I have a tray temperature controller that cuts down the that will increase the feed, because the temperatures are going up, it will increase the feed. And so if the distillate rate is increased, you start sucking in more feed. Yeah, so that's how this thing is going to work. And dynamically it is fast because level goes down, increasing the steam will cause an immediate increase because uh, paper will reach in a few seconds to the top. On the other hand, liquid reaching down will take many minutes. Okay, so the vapor reaches the top in a few seconds, so that will immediately reflect in the column pressure, and then the column pressure controller will crank up the condenser duty and the condensate rate will increase, and that will cause the reflux drum to fill up. Of course, the action of this level controller is nested with the pressure controller. If the pressure controller is on manual, then the level control will not happen because you are not condensing more or less, because you are not adjusting the cooling duty of the condenser. Yeah. Nevertheless, level control will be achieved as long as the pressure controller is always on automatic. Okay, so this is the way this guy works with a nested loop. Level controller is nested with the pressure controller, and that's what is shown here. You've got the level controller there, and now if you look at the specifications, what are the specifications? D, steady state specifications. D, temperature of the column, and L by F. So these are the specs, D, L by F and TS. Let's continue with the last example here. We're going to have a reflux in ratio with the feed, reflux in ratio with the distillate, L by D, because that's very commonly used in textbooks, so I thought maybe I'll use something of that sort. And so D is going to be the throughput manipulator, the set point that I use to change production. So that's going to be this guy, and then I'm going to maintain reflux rate in ratio with the distillate rate, and therefore the only dynamically reasonable way of controlling level in the top is this way. And what that does is it leaves temperature controller this as the only option for temperature control, and I think that's what we show here. Yeah, that's exactly what is shown here. So here in this case we have D, this guy is L by D, this set point, and then we've got T call. These are the three specifications corresponding to the steady state degrees of freedom, and that's what is shown here. There is one point that I want you to note, that in this control structure production rate changes happen by adjustment to Q. In the second control structure, production rate changes happen by adjustment of distillate rate. In the third control structure, production rate changes happen by adjustment of distillate rate set point again. So this is what is used for production rate changes here, this is what is used for production rate changes in the second case, and this is what is used for production rate changes in the third case. In the previous slide, it was feed rate that was setting the production rate. So the point is that where you set the production, that also has consequences on the control structure. But in this particular context of degrees of freedom, specification variables and control structures, the limited point that I'm trying to make is that there exists tremendous flexibility, in fact infinite flexibility, in terms of what you decide to control. Okay, and that's the limited point. And once you've decided what to control, implicit in that specification set is a control structure which one can synthesize using common sense. And what is that common sense? I'll elaborate that later, but the point that I'm making is degrees of freedom specification variables, and implicit control structures. These three things are linked, they go hand in hand. Either you understand all of it or you understand none of it. It doesn't happen that you understand degrees of freedom first and then you'll understand steady state, because unless you understand whether the material balance is closed or not, you don't know whether steady state is going to be reached or not. Your specification set could be inconsistent. That means there exists no steady state for this set of specifications. Okay, or like in the previous case I was talking, under specifying. You think that you're specifying, but there is actually a material balance relationship between those variables, so that's actually under specifying, and then therefore you got actually infinite solutions. The recycled tier will settle wherever you guess it. Yeah, so these are all issues that are there, and I hope these issues are clear. And I want to emphasize and re-emphasize: degrees of freedom, specifications, and control go together. It's a complete package. You can't understand it piecemeal. Okay, that's the point that I was trying to make. Now let's continue. To summarize, if we use simple common sense, it will allow correct calculation of degrees of freedom. The control degrees of freedom is the number of independent control valves in a process, and this control degrees of freedom is further split into steady state degrees of freedom, dynamic degrees of freedom, and fixed operating variables. For example, column pressure, which are fixed, which we are not free to change. So the steady state degree of freedom of a process is obtained as number of valves minus number of non-reactive level controllers that have to be there in the process minus number of specified variables such as column pressure. Okay, as I have been saying again and again, tremendous flexibility exists in what can be specified for the steady state degrees of freedom, and in fact this is what distinguishes a good chemical engineer from a not so good chemical engineer. A good chemical engineer will zero in on good specifications for a given process by inspection, simply by inspection. And it is this insight that needs to be developed by chemical engineers, and I hope that maybe after you've gone through all the material that I have to offer, you will get some sense of how to go about doing it. Specified variables or specification variables corresponding to the degrees of freedom are equivalent to controlled variables, variables that are controlled. And what specification set you use determines if a plant would reach steady state or not. It determines whether all the balances are closed or not. And so therefore what you specify has to be chosen in a consistent manner, in a manner that ensures that all balances are going to be closed. The drifting stoichiometric imbalance, the drifting recycle inventory of the excess component in that toy process example, that's a subtle thing, and most people don't understand that subtle thing. Okay, and so you will have that drifting inventory if you don't install a controller that ensures stoichiometric feed balance based on feedback. And once you decide what are your set of consistent variables that can be specified, a control structure is implicit in it. And how is it implicit? You essentially try to use that control valve that will give the dynamically fastest possible response in order to control that particular process variable. This is called the pair close philosophy. If the control valve that is being used to control that particular process variable or specification variable is close by, dynamic response is going to be fast. If dynamic response is going to be fast, control is going to be tight. So the pair close philosophy allows us to synthesize a control structure that holds the set of chosen specification variables corresponding to the degrees of freedom constant. Okay, so the specification variable set is equivalent to control variables. What set you choose, if it is consistent, the plant will reach steady state. It's very possible that you choose an inconsistent set and then the plant will not be steady, and if you're simulating in a steady state simulator, you'll get spurious steady states, convergence problems, and so on and so forth. and if you are in real life, there will be a drifting mode, a hidden drifting mode, and some inventory will keep building up or depleting, and that will eventually lead to safety issues. And what set of variables you control implicitly assumes a control structure. So in that sense, degrees of freedom, specifications, and control structure synthesis go hand in hand. You either understand all of it or you understand none of it. And in order to understand all of it, an understanding of what are my independent material and energy balances and are they closed or not, that is of fundamental importance, and I cannot overemphasize how important that is in order to understand everything that is of consequence in chemical engineering. Okay, so with that, I think I'll end this lecture. Thank you for your kind attention. Let's find active presenter and close. Yep. Thank you again and goodbye.